Welcome to Fractal Universe. To go to the main menu, press button A on your remote controller. To generate your own fractals, press button B. At any time, if you wish to quit the section you are viewing, press button B to return to the previous menu. No one can deny that fractal images such as this are beautiful, but the question has to be asked, is it really art? Here are some definitions of the word art from several dictionaries. According to the Collins Dictionary, the creation of a work of beauty is art. There seems to be no argument that many fractal pictures are strikingly beautiful. There is no mention in the definition that generation of pictures by computer excludes them from being art. In order to produce plots such as you see on this disc, human skill has been exercised to program the computer and display the pictures. All definitions agree that such skill is a prerequisite. The Oxford Dictionary even mentions technical skill as being a component of art, and there is no doubt that this is present in abundance in the production of fractal pictures by computer. After the picture has been generated, artistic skill can be further deployed to determine the colors to be used in the display. The palette used will have a profound effect on the final picture. For instance, here is a set of variations on color only. The picture elements remain the same throughout. Notice how changing the colors affects the mood of the picture. It is sometimes difficult to imagine that they all derive from the same Mandelbrot plot. Artistic skill is also used to select areas of a plot to be turned into a picture. Here is an original fractal plot as first generated. It might look better if only one side is used. So, we will redraw one side only. The end bulb looks the most interesting, so we concentrate on that. Now the picture is rotated, the outer areas are removed, and the rest left entirely alone, apart from changing the palette. This is the result. What is it? It looks like a lamp. But that's not all. As before, let's change the palette and see what happens. Something quite different. Is it a decanter? It doesn't matter. Each observer might see something different, but the effect is pleasing. It is art. Fractals are mathematical structures of immense beauty and infinite complexity. However closely you examine a fractal, there is always more detail to be seen. Many fractals are self-similar, such as the Julia fractal shown here. Look closely at one of the small curls. The shape is very similar to the larger one, although not identical. Further magnification reveals that even the smallest portion of the original picture is as complex as the original. However far you magnify, you will never reach the end of a fractal. When the first fractals were discovered by mathematicians in the 19th century, they were mostly ignored, regarded as mathematical curios. The problem was that mathematicians couldn't explain their properties. The mathematician Sierpinski discovered one famous fractal, now called the Sierpinski triangle, although the term fractal was not used until much later. Take a perfectly ordinary triangle. The triangle is one of the most stable and most easily defined objects in mathematics. The area is half the length times height, and the circumference is the sum of the length of the three sides. Divide the triangle into 4 equal triangles and remove the internal triangle. You are now left with 3 smaller triangles. Now divide up each of these as before and remove the central portion from each. Now there are 9 triangles. The area is now substantially less than before. Repeat the process indefinitely, and you are left with a ghost image made up of lines. Sierpinski knew there was something odd about this shape. Although it was the same overall size as the original triangle, it was made up of an infinite number of lines and it had no area at all. Many years later, Mandelbrot looked at this shape and asked, how many dimensions does it have? The triangle plainly has 2 dimensions. It has length and height, and it has an area. The Sierpinski triangle has a length and a height, yet it has no area. Mandelbrot found that the Sierpinski triangle had more than 1 dimension, but less than 2. It had a fractional dimension. Mandelbrot soon discovered many other fractals, and realized that fractals were present in nature too. Mountains, clouds, plants, waves, snowflakes, trees. Almost everything in nature is fractal. The closer you look, the more complex the object becomes. Simple mathematical formulae can mimic nature by producing realistic ferns, mountains, and clouds. Mandelbrot went on to discover a method of working out the fractional or fractal dimension of such objects. Fractals can be roughly divided into 2 types. The first type are called repetitively generated. These involve a pattern being repeated indefinitely. Repetitively generated fractals have an initiator and a generator. If we take the Sierpinski fractal as an example, the initiator is a triangle and the generator is a triangle with the center portion removed. The generator is applied to the initiator. This will cut out the center of the triangle. Then the generator is applied again to each of the remaining portions. After 3 or 4 generations or iterations, you are left with an image of the Sierpinski triangle. The other main type of mathematical fractal are called complex plane fractals. They are all plotted on the complex plane using complex numbers. Complex numbers aren't that complex, really. The term is used because each number has 2 parts. Here is a picture of the complex plane. Think of it like a map. Each point on the plane will have 2 reference numbers, one from the scale going across called the x number or real number, the one from the scale going down called the y or imaginary number. Don't worry about these terms, as they are not important from our point of view. We give them here so you can understand references mathematicians make to the real and imaginary axis. This point here represents a complex number of 0, 0. It is at position 0 along the bottom and 0 up the side. This point represents the complex number minus 0.2, 0.5. You can see that we can choose a point anywhere and give it a complex number position, even though it may involve several decimal points. In fact, there are an infinite number of choices. Let's draw one type of complex plane fractal, a Julia set. For this we use the Julia formula, and first of all plot what will happen to one dot, say the top left-hand one. We use Z as the complex number representing that dot, and C as the point on the plane for which we plot the Julia set. Off we go and cycle through the formula, putting the answer back into the beginning for a set number of times or iterations. The number of iterations is not fixed, but the more times we do it, the more detailed the picture will be and the longer it will take to generate. We then move on and plot the next dot on the screen using Z as the dot's address. Let's plot the Julia set for the complex number 0, 0. The Julia plot for 0, 0 gives us a black circle. Let's try another point. Move out of our range as they are being iterated. It's the same Julia plotted in color. You can see Julia's plotted from all over the plane and in many, and use the position of the dot he was plotting as one of the most complicated mathematical structures known. By zooming in and plotting different areas with very fine precision, some startlingly beautiful pictures can be found. The depths of it will never be fully explored, as it extends to infinity. There are many different patterns to be found in the Mandelbrot set. This area is known as the seahorse tail. We don't need to stay in the set color shown. Here is the same picture, plotted with different colors. Each time we zoom in further, the area of the complex plane we are looking at is magnified. This means that we need to use more and more accurate mathematics. We also need to increase the number of iterations in order to obtain detailed pictures. At very high magnifications like this, it may take several hours or even days to fill the screen. We have plotted a large selection of such high magnification fractals for you to see. They are included in our art gallery. Ever since the dawn of modern science in the ancient civilizations of Greece and the Middle East, people have tried to explain the universe in simple terms. Pythagoras discovered the 5 perfect solids, picked up a pebble, and wondered how it's irregular. Johann Kepler was born in 1571. From his youth he was teaching mathematics. He discovered that by inside the orbits of the planets in between the 5 Pythagoreans saw it. 2,000 years progression of the known is God himself. He thought that his limited aspirations of the Danish astronomer Tycho Brahe. From Kepler's point of view, this made things worse. The fact that he had discovered one of the most important discoveries in astronomy in 2,000 years was little consolation. Geometry had failed him. A problem. With 2 planets of the same mass, working the gravitational attraction between them was easy. At any point, the gravitational field would attract an object to one of the 2 planets. The area of gravitational attraction for each planet is easily defined. With 3 or more planets, it suddenly becomes more complex. Using approximations, Newton was able to prove that in the areas immediately around each planet, a point would be attracted to that planet, but in the space between the 3 planets, there appeared to be a chaotic region, where the final outcome could not be predicted. Fields. Helge von Koch was a Swedish mathematician. By magnifying a small portion of the shape, we can see that it is identical to the whole shape, to be known in their lifetimes. The result is put back through the formula several times until square it and add the constant to it again. The advent of in 1936, sensing the coming of the Nazi threat, the Mandelbrot family moved to Paris, where the young Benoit came under the influence of his mathematician uncle. When Hitler advanced into France, the family broke up, and Benoit spent most of the war years living in Toul, a town in the central France. He had little formal schooling, but was guided by teachers often themselves anxious to avoid the attention of the Nazis. He was never an elderly French mathematician, Gaston Julia. In 1954, Mandelbrot emigrated to the USA of Great Britain. Larger result. Rather than settling down to an approximate value for the length of the coastline, Mandelbrot found that the smaller the lines used to measure the coastline, the larger the value he got. The coastline of Britain was infinitely long. Mandelbrot looked again at the Sierpinski triangle. Here was a finite triangle, one of the most stable forms of 3. But what about the Sierpinski triangle? How many dimensions does this structure have? Not 0, not 1, not completely 2 either, because it contains 0 area. It appeared to be somewhere in between 1 and 2. Mandelbrot could immediately see that he was on the right lines. The idea was a brilliant solution, and he went on to define ways of working out the dimensions of all such figures. They all had fractional dimensions. One day in 1975, while helping his son with his Latin, were far less detailed than those seen here. One Mandelbrot discovered his set was a guide to all the Julia patterns. Every point on the Mandelbrot picture can be used as the constant value for the Julia. Many books and films have used fractals to create whole alien planets. NASA has used similar technology to produce an fractal formula. This could allow video phones and full motion video from a compact disc to become a reality in the very near future. We begin our journey with a view of the whole Mandelbrot set. The box shows us the area we will magnify for the next picture. At greater magnification, we can see greater detail than before. We will place our box on an apparently insignificant three-way junction. On magnification, we see that there are several miniature copies of the Mandelbrot set dotted around. There are, in fact, an infinite number of these miniature copies, each of them slightly different. We carry on and zoom into the center of the junction. Again, we see more miniature Mandelbrots, which, although tiny, are as complex as the entire set. Each of these small Mandelbrots is connected by thin filaments. Let's have a closer look at one of these miniatures. Note that this Mandelbrot is pointing in a different direction to the main set. In again, deeper and deeper to view the heart of this Mandelbrot. Our magnification is so great now that we are losing definition and accuracy. We can redefine the accuracy by setting a higher number of iterations. Now the inside of our miniature Mandelbrot is clearer, but it would be clearer still if we changed the colors. That's better. We can now make out the detail of the small Mandelbrot without difficulty. We will zoom in again to look at the tip. The tip is made from thousands of tiny filaments branching off from the miniature Mandelbrot. We will magnify one of the three-way junctions near to the tip. Again, the picture is a little hazy, so we will change the colors to improve this. Now we can see a picture similar to the three-way junction we saw near the beginning of our journey. Small dots surrounded by clusters of filaments, all connected together in a line. We will look at one of these dots a little closer. What we find at the center of this junction is a strange object which looks rather like two single-celled organisms with a dot in between. We will have to investigate this further. Two cells and a dot itself. Each of these cells is similarly subdivided. Anything we have seen previously. Let's magnify this star. Now the long, thin, single cell shapes are back, 4 of them surrounding another central dot. Keeping on course, we will zoom into the center. Now there are 8 thin cells surrounding a central black circle. Once more we will magnify the central portion of the screen. The central circle is slightly oval in shape and does not look original, but microscopic times. If we now scale up the original Mandelbrot to the same magnification, how long would the complete picture be? Well, if we place the Sun at the tip, then all the planets up to and including Jupiter would be contained within the set. Now you have followed our voyage, why not try one of your own? Each journey is different, and if you go far enough, you will almost certainly view fractal images never before seen by man. Select the Mandelbrot program from the fractal generators to start your voyage. There is fractal structure in almost everything in nature, from the largest spiral galaxies to the smallest snowflake. Here are a few pictures that show some of nature's fractal beauty.